it's my pleasure to have you here. Matteo is a great friend of mine. He's a great researcher from Politecnico di Torino. And let me just read your short CV, which is actually really short for the long way you have. So Matteo took his master's degree in electronics in '86 and his PhD in computer engineering in 1990, both from Politecnico di Torino. And since 1990, he's with the DAWIN, the Department of Control and Computer Engineering of the Politecnico di Torino, where he's currently a full professor. He leads a research group working on test and fault tolerance design of ICs and systems. He published more than 400 papers on these topics and is involved in several research projects with companies and public bodies. He's also a fellow of IEEE. So this is probably the shortest CV, Matteo, I've seen so far, and it doesn't say everything about you. Matteo is a huge researcher. He could have a one-page abstract, a short CV here. Matteo, thank you so much for accepting. It will be really nice to hear your presentation in field tests for safety critical automotive devices. And please, you can start whenever you want. Thank you again.
Many thanks, Rodrigo. You are always very kind, and hello to everyone. Thank you for devoting your time to listening me. I will try to interest you and provide you with some interesting information. First of all, before starting, let me thank the organizers, in particular Professor Ricardo Reis, for inviting me to give this talk, and many congratulations for these events, this series of events. I think they represent a very good example of how we can provide precious information to the community at large, gathering people, experts from all around the world, and distributing this information pieces through all around the world. The only drawback is that in this way the workshop is not held in Porto Alegre, and so we cannot visit the nice Porto Alegre, the gasometro, and the lake. But sooner or later, I'm sure the situation will improve and we will be able to meet again in that nice place. Now let's come to the talk. What I am planning to do today is to make a short summary in the next hour of my view of a topic which is rather hot at the moment, concerning the solutions for testing in the field the many safety critical devices that you can find in our cars and in the future ones. Now, this is clearly a hot topic both from an economical, a practical, and industrial point of view, but also from a research point of view. And there are many colleagues many research groups working on this topic. And during the talk, I will first try to show exactly what I mean by in-field test of these devices. I will highlight why this is a very important topic. I will summarize the main techniques for solving this problem, for attacking this problem. And finally, I will mention some of the hot topics, some of the research challenges existing in the area today, in that area today. Okay? So let's start, first of all, from the motivations, because I think it's important to understand exactly what we are speaking about. Well, the whole problem starts from, let's say, the growing importance of functional safety. Now, what is functional safety? We know that safety is one of the attributes of dependability. This is, let's say, the definition according to the, let's say, standard definitions of dependability. Apart from, let's say, the academic definitions, we now have a set of standards, including 26262 for automotive, defining functional safety. And as you can see in the bottom, I also reported the definition by Wikipedia, which is basically taken from TÜV, which is a certification authority. The functional safety is the absence of unreasonable risk due to hazards caused by malfunctioning behavior of electrical and electronic systems. So here you have the key components of the definition. From one side, there is the source of the problems, faults. Faults affecting the hardware, but also affecting the software, bugs, basically. These faults may produce failures. So the fault is the source of a misbehavior in the behavior of a device or of a system. These failures may be classified according to their severity of their effects. Some failures can be tolerated without problems. Some others are really critical. And clearly, combining the probability of faults with the criticality of their effects, I have the risk. Now, when speaking about functional safety, we are speaking about all the techniques for, first of all, evaluating and then mitigating the risks related to this phenomenon. Now, it is important to state that the importance of safety and the functional safety stems basically from the fact that in the last few decades, electronic systems are increasingly adopted in many areas which can be easily categorized as safety critical. And so there are now many standards, many regulations, many laws also that mandate quite severe, let's say, constraints for the development, for the assessment, for the deployment, for the maintenance of all these systems. And in the transparency, you can see some of them. The complete list would be much longer. In this presentation, I will often refer to 26262, which is an ISO standard, which is continuously updated, which is a reference for the automotive market. And practically, if you don't match the requirements of the standard, you are simply out of the market. So it's really important. Now, let's start from the reliability evaluation, because in this way we can understand better where the problem of in-field test stems from. When evaluating the reliability of an electronic system, there are different steps. The first step lies in estimating the probability that a fault occurs. So faults are the causes of failures. Here we are focusing on hardware faults, so defects affecting some hardware component in an electronic system. Now, based on the manufacturing technology, based on the environment, based on the stress the system is subject to, we can estimate the probability that a fault occurs inside this device. And there are techniques more or less standardized, providing us with estimations of this probability. This is, however, let me underline this point, the probability that a fault occurs inside a single device. Okay? Then clearly we need to combine this probability for knowing which is the probability that a fault occurs in the whole system we are considering. This is simply the probability for a fault to occur. It is normally measured in terms of fits, which are the probability that a fault occur, and it is normalized over 10 to 9. So 1 fit means that this device is likely to be affected by 1 fault in every billion hours. Now, this seems a huge amount of time, but remember that many devices are deployed in large numbers. So if some device is deployed in 1 million pieces, which is common in the automotive market, this means that out of all the cars having this device, this will happen every 10 to 3 hours. And this starts becoming something interesting. So it is a measure which nowadays takes very small numbers for a very specific reason. Once we know the lambda, we need to categorize failures according to their criticality. Until now, we were speaking about faults, origins of problems. Now we are categorizing failures. A given system may fail in different ways. Some ways can be tolerated, some misbehaviors can be tolerated, some others less, some others cannot be tolerated at all. It depends on the application and where this system is used. Then we need to link faults and failures. We need to understand every fault which failure may produce. Which is the purpose of this operation? The purpose is to understand which are the most critical faults, because those faults that are likely to produce a critical failure are those we are particularly interested in. And for doing this step, there are different solutions that may be sometimes combined. The most common one inside the automotive market is the FMEA or FMECA, where the C stands for critical. And this is also important to understand. And you link the two. And you can imagine that for a big, complex system, this operation is particularly complex and critical. Until now, I hope everything is clear. In this way, we can have an estimation of the risk and of the reliability of my application. But obviously, inside an application, inside an electronic system, there are fault detection mechanisms and also fault tolerance mechanisms. So it is true that we have some probability of faults, but we have also countermeasures that allow us to, let's say, protect my system, to harden my system against the faults, and there are other solutions based on testing for detecting a fault. Now, this is crucial because if I can detect the fault before it produces a failure, well, I can mitigate the effects of this fault. And from this point of view, you can start understanding probably why in-field test is crucial in safety critical application. To better underline this point, let me use this picture. Now, clearly, our goal, our dream, I would say, is that all the components in an electronic system and the electronic system by itself is perfectly working in a fault-free manner when it is deployed, when the production ends, when the system is assembled and delivered to the customer and then to the user. This depends, how much this is true depends on the end of manufacturing test. Okay, let's assume in this graph, this is the assumption that at time zero, we perfectly tested our system and all the products coming to the user, coming to the car, mounted on the car are perfectly working. Okay, so the failure probability is 0 at time 0. But then, obviously, due to the aging, which is a, let's say, normal and well-known characteristic even of electronic devices, not only of humans, the probability of failure increases. Okay. Now, here it seems that it increases in a linear time, in a linear manner. It is not given; it is just for simplicity, but it increases. The more time you wait, the higher the probability that a fault occurs. Even in a device, in a system which was originally good. And what happens is that in this way, while time flows, the failure probability increases until a given time in which I may perform a test. So let's assume that at a given time, I will perform a test of all the devices in my system, of the system itself. Let's imagine this system is perfect. If this test is perfect. If this test is perfect, at the end of the test, I will be sure that the system is fault-free. So once again, the failure probability will go to 0. Now, let's imagine that this test is not perfect. So it will only cover 90% of the defects or for the faults. Let me confuse the two things at the moment. In this case, the failure probability will not go to 0, but then after the test, will start increasing again. Now, this is crucial. This picture is crucial because it allows you to understand that it is important to test periodically or from time to time our electronic system, because in this way we can, let's say, top the maximum failure probability that we can achieve. And what is typically done is to define the maximum failure probability that we can, let's say, accept. And then we will know in the system, knowing how much it ages, how much the failure probability and how the failure probability increases, we can decide how frequently the test should be done. But this is a test which is performed in the field during the operational phase. And you can also understand how much important it is to devise an in-field test which reaches a given fault coverage. Now, in-field test. Let's speak about this topic, which is the main topic. In-field test has nothing to do with the countryside. It is just a joke here, and it can be performed in different ways. In the simplest version, it is simply performed at the power on or power off at the reset. So let's imagine the automotive domain. A car typically, let's say, stays during the night in a box, in a garage somewhere. Then in the morning, we will turn it on. We will power it on. At this point, all the control units will be tested. This is the power on test. Okay, but for some control units which are particularly critical from the point of view of the safety, this is not enough. We need to perform some tests during the operational phase. And we can perform it during idle times. Very often the applications are cyclic applications, reading sensors, processing the data, and then sending commands to the actuators. From one iteration to the other, there are some idle slots in the order of milliseconds, and we can use these slots for running a test, or even periodically, or when special events occur, for example, a given amount of errors are detected. Now, we distinguish between power on cell test, which is an offline in-field test, because the application is not running at that time. The car is still steady, and the functions are not provided by the different control units. While in the other cases, we are speaking about online in-field test, because the test, it is crucial that does not interfere with the normal applications. And this distinction is very important. Be careful, because in this discussion, we are referring basically to permanent faults. Okay, so we are not speaking about bit flips in the flip-flops. This is another story, and these faults are, let's say, mitigated in different ways, typically through fault tolerance approaches based on redundancy. Here we are speaking about permanent faults. For example, for logic blocks, we are basically thinking about stacked faults or transition delay faults. These are the categories. But permanent faults. With the in-field test, they can detect permanent faults. Now, in-field test is rather different than the end of manufacturing test. Why? Because when you consider end of manufacturing test, the typical procedure is to take the device under test, to place it on a tester, an ATE, and then the tester has the full control of on the device. It can apply whatever stimuli to its inputs. It can fully observe the outputs. The conditions are controlled by the tester: temperature, voltage, power, frequency, whatever. Okay. And this test, the end manufacturing test, is done typically by the semiconductor company, knowing everything about the test, about the device under test. If we move to the in-field test, the situation is rather different, because the device is on the board, and the board is in some box which is placed somewhere in the car. And we need to test all the devices in these boards without removing them from their location, without resorting to any tester, because perhaps the test is performed every 10 milliseconds, and we need to test all the devices. The only solution for doing that is to ask the devices to test themselves, or to ask the system to test itself. So it is a self-test. Be careful, because especially if the test is done online, this kind of in-field test should be particularly well devised and well designed in order not to interfere with the application. So it should be very careful in matching the time constraints. Should finish when the application should start again if it is run during the idle times. Should be very carefully written so that it does not interfere with the memory content of the application, of the status of the system, so that its intrusiveness is very limited. So it is very different than the end of manufacturing test. It has several additional constraints. And here I just reported an example of a control unit for controlling the engine, which is then placed into a box here, and then the box is placed in the car close to the engine. And we need to test the board when being in this position. Now, the devices we are speaking about are very often system on chips. Okay, so devices are composed of different modules, including CPUs, including interfaces, including analog and mixed signal blocks, including memories. And what we need is to test each of these blocks together with interconnections. And for the purpose of in-field test, we need to test them in their operating conditions. So while the system is in the system. Now, this problem of in-field test is not new, in the sense that since many decades there have been systems, electronic systems used in safety critical applications that we had to test in the field. And I mentioned here nuclear plants, military application, space application, aircraft, and so on. But be careful, because these are application domains which are very different than automotive domains. The time to market is much longer, the money constraints are looser, the performance requirements are less strict. There is a strong main contractor that may control everything. So it is easier, it was easier, and in this domain it is still easier to implement in-field test. Then at a given time, electronics started to be used in automotive. The first real application is this EEC developed by Ford and, let's say, used in cars starting from 1975. But be careful, it is interesting, I reported here the complexity of the processor, 2800 gates, and the, let's say, semiconductor technology and the size of the memory. This is really, let's say, Stone Age with respect to today. However, starting from the 80s and the 90s, electronic systems started to be used in safety critical applications. Cars, biomedical applications, pacemakers, trains, all these things. However, in this phase, what was done was to use mature semiconductor technologies so that the reliability can be ensured by the simple fact that, let's say, the probability of failure of faults in these technologies was very low. And so the problem could be solved in this way. Now the situation is very different. It's very different because now, even in the automotive market, we cannot use mature technologies anymore. Why? Because we are going quickly towards autonomous driving or semi-autonomous driving. And we already have applications like automatic parking, collision avoidance systems, pedestrian protection systems, all these systems that do collect a lot of data from cameras, from radars, from LiDARs, and do process them in real time with a very, let's say, huge computational requirements. This is the reason why we need a lot of CPUs. We need the GPUs to implement artificial intelligence algorithms. So we need advanced technology to perform all these tasks in real time. And let me show you an example corresponding to this device, which is going to enter mass production next year, which is a typical device for ADAS applications. It has been designed by Mobileye, which is now part of Intel. And it is a device for supporting others activities, in particular processing camera data in real time. So it is equipped with a huge number of CPUs and GPUs, providing a 12 tera operation per second computational power. You can imagine, okay? And so the result is basically that this will be produced in a 7 nanometer FinFET technology. This is not mature technology. This is very advanced technology. And the big problem is that this very advanced technology is quite prone to defects. Now, if this technology is used in a mobile phone, okay, we are not happy if it stops working, but we can tolerate it. If it is used in something driving our car, controlling our car, we cannot accept it. So we need to target the highest level of safety, and we need to test it continuously. This is the kind of problems we are speaking today. Now, the other important aspect is that the automotive market is characterized by the fact that there are multiple players. Multiple players corresponding, first of all, to the car makers, okay, that try to control what is inside their car. But car makers do rely on tier 1 companies, suppliers like Bosch, TRW, Continental, Magneti Marelli. There are many producing the control units, and these tier 1 companies do rely on chip manufacturers, semiconductor companies, to produce the devices. With very specialized ones like Infineon, like ST, like NXP, like Renesas, or very general ones like NVIDIA when it is necessary to use a GPU. And these tier 2 companies do rely on core providers like ARM. So it is a very complex scenario, and the real question is, but who is in charge of developing the input test for a control unit in the automotive market? Most probably the tier 1 company, because it is the only one having the system view. But this company does not know exactly what is inside the devices composing the system. And clearly the semiconductor companies will never provide too many details about how they implemented their devices. So the key problem here is how to allow the system companies, the tier 1 companies, to develop an in-field test which is able to match the 2662 constraints while getting the information they have, while using the information they have from semiconductor and core providers, so that they can guarantee a given fault coverage. You remember, the fault coverage was crucial to guarantee a given failure probability. This is the issue we have in front today. Now, clearly, one solution is to rely on relatively mature fault-tolerant techniques. Okay, we can triplicate everything, and in this way, we will mask every fault effects, every failure. Or we can duplicate and perform checks like it is done in lockstep, which is very commonly adopted. However, these solutions clearly have a very big drawback. They are expensive, okay? So they are expensive, they require duplicating or triplicating the hardware. Be careful, because another hidden disadvantage is that what we want to achieve here is basically the possibility of relying as much as possible on commercial products not necessarily developed for the automotive market. This would be very nice. So imagine the GPUs. It would be very nice to be able to use the GPUs used for other applications, even in the in the automotive domain. But these GPUs are clearly not equipped with these fault-tolerant solutions. Obviously, there are companies producing devices specifically implemented, specifically designed and manufactured for the automotive market. NVIDIA produces a special version of their GPUs, which is called Javier, which is particularly reliable, but clearly the cost is higher. So the target is to be able to develop solutions that can use commercially available devices developed even for other domains. And obviously, the solution is never based on a single technique, but on a combination of techniques. Now, when addressing from a technical point of view the test of the infield test of devices, let us speak in particular about logic cores. There are basically two solutions: the structural approach and the functional approach, and then some hybrid can be devised. The structural approach is based mainly on resorting on the same solutions used for end of manufacturing test, which is very wise in the sense that all these devices are tested at the end of the manufacturing. Why not to reuse the same solutions for in-field test? And in particular, the end of manufacturing test is strongly based on design for testability. So the circuit is modified, resorting to scan, resorting to BIST, in such a way that it can enter a test mode, and in this test mode, it is easier and more feasible to test the device itself. This is perfectly feasible. It is a nice solution. Clearly, we need to check whether the defects which are detected are enough. In some advanced technologies, it is not enough. We need to introduce a sort of functional test, which is the so-called system level test, to achieve a sufficiently low defect level. But this is another story. But this is the typical solution. The structural approach is the typical solution adopted for end of manufacturing test. Okay, and in this field, what we do with our system on chip is to develop a test for every module based on structural test. Then during the test, to connect to access to all modules. There are standards like 1500 and 6087 for doing so. And then from the outside, we access to this network of modules. We activate the test, we retrieve the results, and we know whether everything works fine or not. Now, this is fine. It works. And the EDA companies do support that. So there are many commercial solutions automating the whole process. Here I'm referring to the one by Mentor, but Cadence and Synopsys have something similar. And what is done is, first the system is moved into test mode, then the test controller, some test controller takes the control of everything, and the test is performed, and the result is then provided. Even for in-field test, EDA companies provide automated solutions. For example, Mentor provides the possibility of including into my device what is called post controller, power on cell test controller, which is able, when activated, for example at the reset or at the power on, to take the control of the system and to run the test of every core inside the system. Perfect solution. Now, this can be clearly done. It is done in many cases with some limitations. This is perfectly suited for a power on cell test. It has some costs because this DFT increases the hardware cost, but we may imagine that this cost has been paid already because we adopted that for end of manufacturing test already. However, be careful, because the main problem is when we try to use these solutions for online in-field test. Let's imagine we have an idle time of 10 milliseconds, so we want to test our system. These solutions are not able to match these constraints, because these solutions are very disruptive in terms of status of the system. They modify the content of the flip-flops of the memory. So what we need when activating this test is first to save somewhere the status of the system, of the flip-flops, the registers, etc. Then to run the test, and when it is finished, and it should be sufficiently short, we need to resume, to restore the status of the system. Can we do that in 10 milliseconds? Very often not. We can divide the test in many chunks, but this is not easy, and this is the main limitation at the moment of these techniques. So, to summarize, structural test is a very good solution. EDA tools available, we can guarantee high fault coverage, but there are some limitations. And let me say also that there is another limitation related to overtesting. Because in these solutions, we move the system into a special test mode. And in this test mode, we may test even defects that are not affecting the normal behavior of my system. And we will speak about that better in the next minutes. Let's move to another solution. We spoke about the structural approach. Now let's speak about the functional approach. Now be careful about the definition. The traditional definition of functional test and that we probably have in mind is a test which does not address the structure of the circuit, the stacked faults, etc., but something testing the functionalities, whether the different functionalities of the device or of the system are correctly implemented. Okay, in this case, this is not the scenario. When speaking about a functional test here, I'm speaking about something which is simply not using design for testability, not using the structural approach. So we are not using scan, we are not using BIST, we are just forcing the system to work in its normal mode, okay, without moving to test mode, without reconfiguring it. So acting on the functional inputs and looking at the functional output, okay? Now, it is clear that this is compatible with the generation of some stimuli that can then be fault simulator, and we can gather a fault coverage in terms of structural faults, stacked faults, transition delay faults, if I can perform the fault simulation. And normally I can do that apart from the computational effort, okay? So this is the definition of functional test that we are using here, okay? Which is reported here. The nice thing of this functional test is that it does not require any tester, because very often it means just applying some normal values to the inputs and observing the outputs, and it requires limited resources, and it can be modified easily, okay? Now, clearly, this functional test is something similar to the sequential test, which was very popular in the 80s and in the 90s, but we had some crisis because it is difficult to devise an effective sequential ATPG. However, in this case, we are in a special case because we are speaking about devices, our SOCs, that normally include one or more CPUs, okay? Now, in the case the system includes a CPU, what I can do is to force this CPU to execute a given test program. And this test program is in charge of exciting possible defects inside the CPU module or inside any module inside the system, and then check the results. Now, this is based on software because it is based on forcing the CPU to execute some program. And in this way, the test tests itself. So it is a self-test, hence the name SBST, okay? Now, in order to implement this kind of test, what we need is to first devise this test program, and then at the application time, this test program must be stored inside some memory accessible by the CPU. The CPU should be told to execute it, and then we need to check the results produced by this code. If the code is suitably written, I can detect quite a lot of faults. Now, this approach has been adopted quite intensively in the last years by many semiconductor companies. Because in this way, what we can do, what we can achieve, is a situation which perfectly fits the scenario of the semiconductor, the automotive market that I described before. So let's imagine a semiconductor company producing a device that may be used in a safety critical application. They will develop a set of test programs, what is called a software test library, to be sold to the customers using this device for a safety critical application. This test library has been developed by the semiconductor company, who knows exactly what is inside that device, that can perform the fault simulation, that can guarantee that this piece of code achieves a given fault coverage. Now, the tier one company, the system company, when deciding to use this device, will also buy this test library, and will include this test library in the whole package of the software stored in the flash on board their system. And from time to time, depending on the criticality, depending on the characteristics of the system, these test libraries will be activated, will achieve the specified full coverage that we know it is guaranteed by the semiconductor company, and we can achieve the reliability target we are interested in. So this system, this mechanism fits very well the automotive market requirements, and it has been used by many companies. Here I reported some of those that definitely use this mechanism and provide to their customers these self-test libraries. Now, clearly be careful, because these test programs are then stored in the flash together with the application code. Now, this means that, first of all, there is a cost, because the flash should be a little bit larger, and I will pay that. Moreover, this means that the self-test library, the software test library code should also match all the requirements for the application code. So it should be written in a very careful manner, complying to all the standards. Then the test program, it is launched. In many cases, it is launched by the operating system that sees the test program as a set of routines to be activated when required, whose results should be checked because it tells you the health status of my system. And let's say the results can be observed either checking the results produced by the test program in memory or by computing some signature. There are many techniques. The key problem here is the test stimuli generation, the test program generation. This is the big problem of the functional approach. Why? Because for the structural approach, I told you that there are good and mature solutions, commercial tools. EDA companies invested a lot and are very happy to sell you tools able to introduce scan chains, to introduce a scan beast, to support their usage, etc. This is not the case for functional approach. So the test programs should be written typically manually by teams of skilled designers and test engineers. Okay, so there is a cost, definitely a cost. However, be careful, because this cost, when this process is well structured, can be limited, although it is significant, because the process cannot be automated. And the return from this investment, however, can be quite long, because these devices are not sold for 6 months, like for the mobile phone markets. They are sold for longer periods, because the automotive market is a more, let's say, stable market. So, for example, ST Microelectronics developed one of the key products is ST32. ST32 is a microcontroller for which these self-test libraries are available, but the investment for producing them is, let's say, is returned over a long period, because ST32 will be sold, has been sold for more than 1 decade now, and will probably sold in the future. So, I mean, the situation is different than for end of production test. There have been, there are quite a lot of techniques for helping these groups of people manually writing these self-test libraries. In particular, there are techniques described in the literature for developing suitable test programs for testing each unit inside the CPU. So there are techniques for testing the arithmetic units, for testing the branch prediction units, for testing the caches. I mean, for every unit which is typically existing inside a microprocessor, a CPU, there are solutions for describing how to write a suitable test program for that. There are also efforts to automate the generation of these test programs, but until now there are no commercial tools. Okay, so there are, for example, formal techniques which have been used and successfully proved to be able to, at least for medium-sized processor, to generate these test programs, but still there are no commercial tools. Let's hope they will appear in the future. So currently, the cost for creating effective self-test libraries is the main drawback of the functional approach. Now, to show you that I'm not speaking about academic, let's say, games, but about a real, let's say, practice, Let me comment with you this table where I tried to summarize some processors, some processor cores for which we developed self-test libraries, either by ourselves or in cooperation with STM. As you can see, some of them are, let's say, academic models which are available, open source available. Others are STM products for which they developed these self-test libraries with our support. Now, this test program have been developed for stacked faults. Here I reported the achievable full coverage, and here I reported also the duration, because you remember the time constraint is a critical one in this area. Remember that one of the advantages of this approach is that it is much less intrusive of the structural approach. There are 10 milliseconds of idle time. I can run a small procedure testing one piece of the CPU, and then I will gather the result. And this can be done, for example, by the operating system launching the test program. So this is the overall duration, but the self-test library can be split in many chunks. And obviously the size is also important because it requires, let's say, some flash size, some flash space to be stored. Now, what you could say is, yes, but the full coverage in some cases is not so high. Now, the problem is that you need to take into account safe faults. And this is the next topic I want to cover with you. You remember the basic picture I showed to you. From time to time, the failure probability increases. From time to time, you need to run a test. And the effectiveness of this infield test depends on the achieved full coverage. However, there are faults that are guaranteed not to produce any failure in the system. Okay? Untestable faults are some of them, but there are others depending on the application and on the system. Let me provide you with some trivial examples. Let's imagine that I'm using a microcontroller including floating point arithmetic, but for some reason I'm not using floating point arithmetic, only integer arithmetic. In that case, all faults inside the floating point unit are not going to produce any problem in my application. So they are safe faults. And there are many cases like this. For example, the faults in the debug unit, I don't care about them because during the normal application, I'm not using the debugger. Okay? Faults affecting the test infrastructures, the scan chain, are not affecting the normal behavior. So they are safe faults. Why are safe faults important? Because I should not take them into account when computing the full coverage for infield test. Because for infield test, what I need is to compute the full coverage out of the list of faults that may produce a failure. Because what I want to compute is the failure probability, not the probability of a fault in general. Okay? Now, if I'm able to identify the safe faults, which is not a trivial task, but can be done, well, in that case, I can remove them from the list of faults to be considered for the full coverage computation, and I can improve the full coverage. We published a paper at the VLSI SOC 2 years ago in which we reported some experiments we did with a real application developed inside a European project for the Ariane launcher. Okay, in that application, we were using an OpenRISC 1200 processor, and here you can see that the number of safe faults in that processor, considering that application, is not negligible. Was something like 13%. And considering these safe faults, we were able to achieve 84% of full coverage with the self-tested library we developed. And this is enough when combined with other techniques that are normally used for functional safety, like ECCs, protecting memories, buses, registers, and so on. Just to give you an example, it is enough to guarantee the level of full coverage that is required. But it is important to underline that safe faults are not negligible in terms. Be careful about another point. If we are using structural tests, even safe faults are considered untested. And this may lead to a significant overtesting, discarding products and, let's say, removing from the operational phase products which are normally working. If there is a fault in the floating point unit, but the floating point unit is not used, well, performing logic based, this is not detected. And so we will discard this unit. And one advantage of a functional test is includes that. So the advantages of functional tests are in terms of flexibility. I can modify the code quite easily if I need to adjust, for example, the fault coverage, or I see some defects are not properly detected. There is no overtesting. I can achieve a good fault coverage if the test program is carefully written. It is not intrusive at all because it is a functional test, and if it's correctly written, it is not intrusive. The duration can be adapted because these test programs can be shrinked and enlarged as well. And it well fits the scenario of the automotive market. The main disadvantage is the development cost, basically because at the moment that there are no commercial tools available. Let's come to the end. Let me, first of all, before drawing some conclusion, let me mention some challenges, some hot topics on which the research in this domain is very active at the moment. Well, first of all, there are quite a lot of techniques for developing self-test libraries for CPUs, pipeline CPUs, I mean, quite a wide range of CPUs. There are quite a lot of activities for extending that to more complex processors, even superscalar processors, multi-core processors, but also to complex peripheral modules. So we recently published something about the functional test of a CAN controller, because CAN controllers are everywhere in automotive, and how to test GPUs. One of my PhD students did an excellent job in developing techniques for testing in this way GPUs, which are now quite common in the automotive market. Then there is the issue of minimizing the size of these test programs and the duration of these test programs. The shorter, the better. There is the issue of attacking delay faults. Until now, most of this work has been done, of the work in this area has been done targeting stacked faults, but delay faults are there, and with these technologies are very important. And some solutions are being developed for targeting delay faults. And finally, security issues. Inside automotive devices, there are more and more pieces of logic dealing with security, guaranteeing security. Testing them is an issue, is a challenge, because first of all, no one tells you how they are designed, what is inside, how they can be used, because I mean, confidentiality is crucial there. But they need to be tested, because otherwise, how can I guarantee the security they guarantee? Okay, so this is another interesting issue. I hope I presented in a comprehensive manner the scenario in the area of in-field test for automotive devices. I hope you understood the specific characteristics, the possible solutions, structural and functional, and obviously the combined solutions. I hope I presented in a clear manner the fact that here we are not speaking only about technical problems, but a mix of technical problems and commercial, organizational problems, which are important. And the role of EDA tools to support a comprehensive and complete design and test flow is clearly complete. With that, I can conclude my presentation with a nice picture of a nice mountain very close to Torino, which is called Monviso, nearly 4,000 meters. And this has been taken at the sunrise. And if you will visit Torino when the virus will be out, I strongly suggest you not to be on the top, quite let's say challenging, but at least to visit the area and to enjoy this location. With that, I'm open for questions from the audience or for comments. Obviously, I'm here for that. And obviously, you can contact me even at the end when this talk is finished for any comment or question.
Matteo, thank you for your great talk. I think it was the perfect mix between being educational and also being technical about the next challenges. So for me, it was the first time it is the first time I hear about software building self-test. I'm not sure why, because it makes perfect sense. I was actually very used to Beast and these tools that you presented from Mentor and Cadence and Synopsys, but never doing them in software.
You can start, Rodrigo.
Yes.
Let's talk about that.
Yeah, and I mean, it makes perfect sense. But my first question is, number one, in order to do Beast, let's say Beast by software, you still need some hardware support, right? For example, you need access to some registers, for example, let's say some operational systems registers, which are not always visible by the software. So my first question is, do you actually need some support from the hardware, or can you kind of write your software around the, or force some data into these hardware registers?
No, at the moment, I would say that there is no support, no hardware support, in the sense that the big advantage of this technique is that it does not require any specific support from the hardware designers. What I'd like to clarify is that this kind of technique, the software-based self-test, exercise the processor, the CPU, using the resources available. So if you need to test a register, you will write some instructions, writing some value there, and then reading the corresponding value and writing it into the memory so that you can check whether there is any problem. So what you are doing is you are exercising in a smart way the different part of the CPU, and then trying to check whether they reacted in the correct manner. Think about an adder. If there is an adder, I will test it by asking the processor to perform many add instructions and then checking the results. Now, clearly, for the adder, this is relatively simple, especially if you have the netlist. If you want to test a branch prediction unit, this is less trivial. Testing a decoding unit, this is less trivial. So there are some units which can be tested quite easily, the register 5, for example. Some others which are challenging, and these are the units which are also quite critical and require a lot of efforts for developing suitable self-test libraries. Now, clearly, in the future, it is forecastable that some hardware may be introduced to support software-based self-test. For example, instead of looking at the results into the memory, it would be very nice to have some monitor looking at what is written on the bus, just to simplify, okay? And something similar already exists for debug purposes. And in some cases, it is used. And in this direction, some more features can be added to our processor in order to better support the software-based self-test, to make the development of the test easier, but also to make it shorter and more compact. So there are works to combine together some hardware with the software technique, okay?
Something like software, hardware, co-design for self-test.
Something like that, yeah, exactly.
This is a great paper title.
Definitely. So we have the title already.
Yes. I have another question, which is about the cost, because you said that one of the challenges is the cost. The cost in terms of memory, in terms of execution time, but you also have a cost in hardware, right? So in the end, you're trading silicon area and also development time for silicon area, for BEAST, for example, even though it is kind of automatic, for software procedures. So how does the automakers market looks into this? Are they open to trading some hardware pieces for software? It seems to me yes, but I think you're the guy to ask this question too.
Well, it is difficult to provide a complete answer, in the sense that it depends. Okay, so it also depends on how much the let's say the semiconductor company designing and providing the device is interacting and is cooperating with the tier one company. Okay, in some cases they are the same company. Think about Bosch. Okay, in some cases they can act on the devices saying, okay, I need to test that in the field, so let's design it in a smart way. But in other cases, think when we needed to test a microcontroller. A microcontroller is very often not designed for a specific application. It's designed for a market. And then it is up to you to use that in a safety critical application or in a normal application. I mean, it depends, but the device is always the same. And in that case, it may also be the case that the semiconductor company does not provide to the system company any information about how to access, for example, the logic bit. So if you ask NXP how to access the logic bit, they will probably not answer to you, nor to me, but not even to, let's say, tier one companies, because they fear that their confidential information may be stolen in this way. And this is another advantage of SBST, because in this way you just provide a piece of code testing the device, nothing else. And activating the code is something very easy, trivial. So it's much easier and it's much more sure. Clear that, someone has to write this code. And this is an expensive task requiring smart people. Okay, so it depends. In some cases, one solution is better, in others, it is not. The real thing is that most semiconductor companies are providing these self-test libraries at the moment, obviously by paying. It's always a matter of money, often a matter of money.
We have a question from Dave. Let me bring it to the stream. He asks, can you account for degradation in the test hardware over the car lifetime for, let's say, 10 to 15 years?
Sure. This is a major problem in automotive because especially when using advanced semiconductor technology, 7 nanometer technology. Are we really sure that in 15 years these devices will still run at the operational frequency they have been devised for? And clearly, what is dramatic is the fact that we know very well that the aging strongly depends on the workload the device is subject to and the conditions. So if the car is run in Texas, it's different than when it is run in Norway. And if it is run by an Italian driver, it's probably different than run by a Swedish driver. Okay, because the workload is probably different. So this is another crucial role of in-field test, to continuously monitor when the device or the control unit is entering the wear out phase. Okay, so we need some solutions so that if we are happy, we are lucky, and the control unit will last for 10 years, okay, fine. But if after 5 years, 10 years, the control unit starts having some troubles, I need to change the control unit, and I need to detect this kind of troubles. This is the reason why it is particularly important to move as soon as possible from stacked faults to delay faults, because this aging is strongly related. It will, let's say, appear by affecting the timing of the control unit. So I think that this is an important, let's say, topic where companies are already investing quite significantly. Aging of the devices.
And one final question, Matteo, on this aging subject, but also on predicting faults. Self-based test, you can detect a latent fault, like an issue. But let's say checking the peripherals and all your sensors, because cars will have much more sensors, right? So my question is, can you somehow predict a fault? This is out of the scope of your talk, but let's just say you have data from all your sensors. Can you somehow predict aging from your sensors? Let's say, can we use some kind of machine learning approach to sort of receiving data from the sensors, kind of predict that you will have a fault in the next, I don't know, 1 month, 1 year, something like that?
Let me say that this is the dream, and several companies are working on that. They also created a name, a vocabulary, which is a prognostic. Prognostic is, let's say, the art or the technology for anticipating faults by looking at how a given component, whatever it behaves. And by sure, in some cases, you can already detect, let's say, the wear out of a given component, for example, by looking at the currents, by looking at the delays, by looking at some, even some errors that from time to time may be caused. So some transient errors may be, let's say, a sign that the silicon is going into the wear out phase. Clearly, this is not easy because it is difficult to model these phenomena, and if without a model, it is difficult to predict. But there are a lot of there are some works on that, also using machine learning, because since we don't have the model, perhaps we can learn from previous cases and try to extract from the data we can get from the devices when the devices do tell us, be careful because I'm getting old and it is probably good to put me in the retirement or something like that. This is definitely a challenging, let's say, topic, not solved at all.
And we have one final question from Ricardo, and his question is: to cope with aging, the layout design should use relaxed design rules. What are your comments on that?
My comment is that Ricardo is perfectly right, but think about the device I showed you at the beginning, Mobileye IQ5. This is designed in 7 nanometers. It includes some, I don't remember how many billions of transistors, and I'm sure it is not designed with a relaxed layout rules. I think it is designed with very aggressive rules. It will run at a high frequency because there is a performance issue behind. So this device is expected to process the data coming from many cameras, to combine them in real time and to detect obstacles in real time. Okay, so my feeling is that these devices are not intended for safety critical applications. They are used in safety critical applications, but not designed for that. And clearly, we need to combine all these constraints, including the reliability ones, finding some way for testing them at the end of the production. This is already not trivial. And then for testing them in the field, achieving the reliability. So Ricardo is right, but I don't have a solution. I don't think the solution is easily reachable. But in the same time, these products are going to appear on the market very soon. Are there already? Because I mean, all the ADAS components are on the market. Okay, even in medium cost cars. And so, I mean, there is quite a lot of activities to combine all these constraints.
And a quick comment, Matteo. This chip you mentioned, it had 12 tera operations. The newest PlayStation 5, which is launching, I think, today and this week, it has 10.5 teraflops. So we are talking floating points against operation. But it's kind of having something like a PlayStation 5 running on your car. So this
this device is intended to perform very advanced functions, yes, like most probably obstacle detection, cruise control, advanced cruise control, things like that. So I'm quite sure that the typical application that will be run on top of it will be some machine learning based on neural networks. And you know, these applications are very computational intensive. Okay, so clearly it is always difficult to understand when they speak about teraflop operations, what they are exactly. But still, it is a very advanced device, compatible in terms of computational power with many GPUs currently on the market. Okay, because these are the competitors. NVIDIA or AMD with their GPUs, Mobileye with these kind of devices. And so, I mean, the computational power is huge, really huge. We don't probably realize that when driving our cars, but we are sit on high performance computer running running us and driving us in the close future, probably.
Yes,
So
perfect.
good. Let's hope.
So thank you, Matteo, again for a great talk. It was very educational and technical, and I think it will inspire lots and lots of people. So,
Thank you, Rodrigo.
Matteo,
Thank you for everything, and thank you, Ricardo, and all the organizers.